Hi everyone. Uh, S- Samir, you can stop the music maybe now. Hi everyone. My name is Praveen Kumar. I'm the founder of Towards Machine Learning.org. We have Samir Koleshwar with us. He'll be presenting on vector space models. So the whole idea of the session is to impart knowledge on vector space models like word-to-vec, glove, fast text. we'll be uh, we'll be starting from the scratch, and we'll be taking you to the advanced level of the topic. We'll be even sharing you the most frequently interview questions asked. We'll be even showing you the implementation of word to back using Python. So without further ado, I'll hand over to Samir to start the session now.
Thank you, sir.
Yeah.
Hello, everybody. I hope you all are safe and doing well. First, I will introduce myself. My name is Samir Kodeshwar. I am currently pursuing my master's in signal processing and machine learning from NIT Surat. Before starting our session, I would like to know how many of you are familiar with the basics of NLP or text pre-processing or something like this. So can you comment in chat window?
We will highly appreciate if you guys could respond to the questions asked, so we can make it a bit more interactive, and we would be knowing what kind of audience we have with us. So that will help us assessing the topic, to what depth we should be going in the topic, and how well shall we explaining the topic. Okay.
Oh,
Okay. Sami, over to you.
okay, thank you, sir. So here I am able to see there are some people are little bit familiar with some basics of natural language processing. So don't worry if you are not aware of these things. I will make sure that I will clear your all doubts, and you will be come to know what are the vector space models and how it is going to use in our daily life where we use NLP. Uh, in this session, first we will look at what are the outlines we are going to cover in this session. First topic is what is the need of word embedding, and then we will see what is a word embedding, or it is also known as word vectors. Then basically there are several models developed in this field. First we will see the what is a word to vec model, and it is basically a family of two architectures. Then we will see that both architectures one by one. One is a skip gram model and other is continuous bag of word model. Then we will see the negative sampling part and hierarchical software classifier, and how it improves the uh, drawbacks, some kind of drawbacks that occurs in skip gram models. And then we will look at the glow model, and and how it is different from word to vec model. Okay, then we will see fast to text and doc to vec models, and then we will see the sentiment, how to do sentiment analysis using these word embeddings. But before start uh, our session, I would like to share this cartoon image here. Here you can see that one cartoon character is ordered for cappuccino, but the robot here is serving the espresso instead of that cappuccino. So but if she is asking why you are serving this, I ordered for the cappuccino, but then the robot tells her that the cosine distance between these two things are very small. He is trying to say that both are same kind of things only, but do, uh, but how the robot can understand our human language, it is very unstructured. So it is very means that we will see in this session, that how the robots will come to know our human language. And you also come across the similar kind of scenarios when you are using some conversational agents like Google Assistant, Siri, or Alexa. Means when you are interacting with these uh, uh, applications, you ask them to do one kind of thing, and sometimes they misinterpret what you talk, and do some irrelevant stuff. But actually, do you know how these conversational agents works? Means how they recognize our speech, how they analyze the language, and uh, extract the information from web, and after extracting information, they convert that text into a speech, and uh, tells us the answer, or whatever it performs the task. So it is very fascinating thing. Okay. So now we will see some of the applications that we are going to use in our means that we are uses in our daily life. First, here you can see one a keyboard here, and here it is suppose you have type here in the message like I will meet you at, and the keyboard is giving you some suggestions, and these suggestions are very relevant as you see this particular text. uh, and here also in a Google search engine, when you type some things at a starting, what is the, and it will give some most search or most frequent search topics. Actually these are the application where actually these applications are comes under the language modeling task in NLP. And there is a one different task uh, which is known as machine translation. In machine translation, basically, we try to translate one language into another other language. So here in this example, you can see that this English sentence is converted into Spanish sentence. Okay, and you also might have observed some chatbots when you place orders on Swiggy, Zomato, or Flipkart. Actually, these kind of chatbots help us at the initial stage to solve our some doubts, and then it will connect to some agents at the company. So basically, this is also based on natural language processing. Okay. So these are the wide areas where the natural language processing is used. But do you observe that in every this application, there is a building block of all these things are words. Okay. Just like in image processing or in a convolutional neural network, we try to extract the information, try to extract the features from the images, where the building block of that image is one small pixel, and it has some intensity value in it. But here we have the words like, and these are the unstructured part. Okay. So basically this kind of thing, we machine don't understand this kind of thing. Means if you want to develop one sentiment analysis model, sentiment analysis model in means we try to develop such a model that we give one particular sentence to it, and it will give us the feedback. Means this particular sentence has a positive feedback or a negative feedback or neutral feedback. Actually this kind of applications are very useful in the restaurants or in movie reviews. or even on a Twitter Twitter comment tweets, we can apply this sentiment analysis and try to extract the what people are thinking about the one particular topic. Okay. So here I have put a one neural network model which tries to do sentiment analysis between the positive and the negative sentiments, and I have given the sentence like I am happy. This sentence is a it has the positive positive feedback. Okay. But how these words or the letters can actually means the computer doesn't understand these words. Okay, it understand only the language of numbers. So our main task here is to convert these words into a numbers. So can you suggest something that can be helpful to convert these particular words into numbers? Can you collect the what kind of technique or what kind of thing can you implement? You can put the answer in chat window. Yeah, tokenization. Actually, tokenization splits our sentence into words, but actually we have to assign these words to some number. Okay, means it's and after assigning those numbers, we should correlate or we should get the semantic meaning from similar kind of words. Okay, TF-IDF. Okay, what to it? Yes. So actually, we are going to see how these words are converted into vectors. Okay, but basically, first I want to show you how you can encode each number into uh, into a some kind of unique numbers. Suppose consider in your data set you have the sentence like the cat sat on the mat. Okay, here first we have to split this sentence into words. So and after splitting into words, we can only put the unique words uh, the unique words here are the cat sat on and mat. Okay, and we can arrange these words into alphabetical order, and we can assign one as cat, two as mat, and so on. And with the use of this, we can encode our sentence as 51435 like this. But the main drawback is of that this technique is this integer assignment is a very arbitrary. Okay, and this 1 and 5 you cannot correlate. Means you cannot find the relationship how it is related. Means how the fifth word is related to the first word. Okay, so it is very challenging for us to interpret, and for the computers it is more worse. Okay, uh, and so that's why this type of features we cannot use. Okay, so we have to so basically the so one value assignment for a one particular word is not sufficient. We have to give the some we have to give every word some representation as a vector of some multiple values in multiple dimensions, so that we can uh, extract the features of that word. uh, okay, so basically you can recollect the one hot encoding technique. In that uh, we try to assign one for that particular word, and all other values are zero. But uh, here I have considered that that previous sentence only, and we have a total 5 unique values. Okay, and so for okay, do you have any doubt? You can ask by unmuting yourself. Okay.
Samir, I guess you are on mute.
Oh, okay. Sorry.
Yeah, sorry.
Sorry for that. Where actually, what is the last point you heard?
You ask people to unmute themselves and ask the doubts. And I'll highly appreciate if participants could unmute themselves to ask the doubts. Otherwise, you can put yourselves on mute if you guys do not have any doubt. So that will help us organizing the session smoothly.
Okay. Okay, sir. Thank you. So I was telling about this one-hot encoding method. So basically, you have these particular words in your dictionary, and you have only five unique words. So to represent every word in your dictionary, you have to create one vector with that size of means total number of words present in your dictionary. Okay. So for the to encode the word cat into a vector, you have to put one at the index of a cat word, and for other indexes, we have to put the value as a 0. And basically, we have to do the same procedure to encode the every word. So basically, the here the 0 are repeating more frequently, and if you take this vector of the and you try to calculate the dot product with a vector of cat, then or any other vector in your dictionary, then you will always get value as a 0. Means these are orthogonal to each other, means you cannot find any kind of relationship. Okay, so this is a main drawback of encoding the words into such kind of vectors. And a second drawback I would like to share you that the size will increase when the number of words increases in your dictionary. So it is very and it is not very efficient way of representing words. So what so how we can solve this problem? So yeah, so word embedding is the way to solve this problem, and it is also known as word vectors. Basically, here we try to represent each word into some n-dimensional vectors. Here, for this example, I have taken the four four dimensions to represent each word. But this can be, I mean, this is a hyperparameter, and you can change, and you can increase the size of vectors. Okay. But consider for this case, we have only put these vectors into four dimension, and we are getting some uh, floating means floating values in our each dimension. Actually, these values are going to come from our training part. I am not assigning for manually these values. Okay, so we will see how this network works, and these values are going to come. Okay, so basically what are the benefits these word embeddings are providing? So it is not a sparse vectors, if you see. Okay, so the value means you can extract the features for the every word in that particular direction, uh, in dimension maybe. And if you calculate the dot product between any two vectors, then you will get some particular non-zero values. Okay, so our main idea is to get the semantic meaning between the similar kind of words with this dot product, so that we can say we can easily identify the what we are trying to, I mean, so from this computer can easily understand what humans are trying to say. Okay, so basically before going into word to models, I would like to share some vector algebra, vector algebra terms here. First is a Euclidean distance. What is the Euclidean distance? Are you aware of this term? You can put in chat window. Okay. Yes. Okay. So I think many of people are aware, but I will cover this topic in short. Okay. So basically, Euclidean distance is calculated. We can calculate the distance between the two vectors. So basically, if you have the vectors at 0.01, 0.07, or and 0.1, means this is one point in 3-dimensional, and the other point is located at a 0.91, 0.57, and 0.6. Then how you are going to calculate the distance between these 2 points? So basically, we are going to take the L2 norm, and L2 norm is the formula of L2 norm is like this. Basically, we are first we are calculating the difference between this point and this value 0.91 and 0.01 and 0.91, and then we are going to square this, and then we are taking the second value 0.07 and 0.57. Then we are subtracting these two values and squaring and adding like this. Whatever we have the dimension, we can do the summation on that n dimensional vectors, and after that we have to take the square root. This is basically our Euclidean distance. But if you see this formula contain means this formula will give only the magnitude. It will not give the direction, but the direction is very important to see what that we will see in next slides. Okay, so our next topic is cosine similarity. Actually, this is a the problem we are getting in Euclidean distance is that the bias by the actually it is biased by the size of the difference in the representation. Okay, so we may decide that cosine similarity would determine how basically it is one of the evaluation criteria to evaluate the vectors. Okay, means if you want to find the angle between these two vectors, woman and man, then you can use this dot product formula, and basically the dot product formula gives we can represent it as the magnitude of v vector into magnitude of w vector into cos beta, and the beta value is the this angular distance between this vector, woman vector, and the man vector. Okay, and this cosine similarity the cosine similarity helps to determine the how the similar text is using means how the texts are similar to each other, and we are doing with the help of this formula. Okay, and so basically when the cosine value is 0, it means that the two vectors are not similar, and they are perpendicular, because the cos 90 is 0. Okay, so the angle between these two vectors are 90 degree, and they are not similar means they are in totally opposite means they are opposite direction. So they are we can say that they are not they don't have any means similar kind of context. Okay, but where for the some cases you will get the cos beta value near to 1. So in that case, we can say that these two vectors are pointing in the same direction, and we can say that these two vectors have the similar kind of meaning. Okay, so this is basically we are going to means our main criteria of our means word to act is mainly depend on this how the how to represent the similar kind of words into a similar kind of vectors. Okay.
Hello.
Hello.
Hi, Samir.
Hi.
Actually, my question is, if the cos theta value is 180 degree, that is -1 value, then in that case, what will happen?
Okay. So in the same case, actually here we will get only a 0 to 1 value. Okay, as the cos inverse range, that is 0 to 1. Okay.
Okay.
So basically we will not get the negative values, but if the two vectors are in 180 degree, then also we can say that it means the direction of that two vectors are totally different and they are not similar kind of words. Okay.
Okay.
Okay. Do you get a one doubt how to represent these words? Okay. So basically here I would like to share this one visualization. Basically consider you have calculated word vectors in 300 dimension. Okay. So we cannot visualize these 300 dimensional points. At the most we can visualize three-dimensional points. Okay. So basically with using PCA dimensionality reduction technique, we can reduce these 300 dimensional vectors into a 2D vector, so that we can plot it into a 2D 2D space. So here I will show you that I would like to show you that it form the similar kind of words are forming the clusters in this 2D space. So uh, you can see the word like 90287 all these means the words represent, means all these words have this similar, means it represent the some value. Okay, count means, and these are forming one cluster in our 2D space. Similarly here you can see the Tuesday, Wednesday, Thursday, Saturday are forming one cluster here. And here if you see this side, then you can see the different kind of different subjects like science study biology, chemistry, statistics, physics, maths, like this. These are all kind of, means all these words are means similar kind of words, and it creating one clusters here. And here you can see Venus, Pluto, Mars, like this. Okay. So now we will see how actually this kind of similar means this is what we will get when we use these word embeddings. Okay. So this is how it is very powerful to extract the feature from the similar kind of words. Okay. So first algorithm is we will see is word-to-vec model, which is developed by Thomas Michelot and his team at Google in 2013. Actually, it is a neural network based model which tries to learn the word vectors. Okay, and it has only one hidden layer. Okay. Actually, word2vec is a family of architectures where there are two types of models. One is a skipgram model and other is a continuous bag of word model. So basically here we have created one fake task. Okay. Why it is why it is fake task, I will tell you that later. But here is our task is to create a here our task is to predict a context words given the center words in skipgram model. Okay. So basically here when I put this word brown, when I put give input as brown to our model skipgram model, then it should give the what are the probability of the quick and jumps or fox rather than all other words presented in our dictionary, because the probability of occurrence of the quick and brown in the same window is more. Okay. Similarly, in second model, in continuous bag of word model, we have to predict the center word given our context words. Means context words means here actually this is one sentence. The quick brown fox jumps over the lazy dog. Okay. And if you gave your model this quick brown, and here you don't give anything, and here again you give this kind of words, then our model should give the probability of coming fox here at a blank space should be means it should predict this center words as a fox. Okay. This is our task in these two different models. So first we will look at how we can prepare the data set for this. It means basically in CNN task you have the images of various various scenarios, like you have the images of cat, dogs, or maybe something like this. But when you are working on a natural language processing, your data set contains only the sentences. Okay. And we have to prepare our prepare that training data in such a way that we can have pairs of our center word and context words. Okay. So basically in this case, here I have considered the window size as a 2. Okay. So consider this blue box as your center word, and for this window size of 2 means from the back side or from the front side, you can pick the words within this particular window. Okay. For this fox word, you can pick quick as context words, context word, or brown as a context word, or jump or over. Okay. So this kind of we have to convert this sentence into this kind of training samples. And actually we have to do this process on entire our data set, on entire our means for our every sentences in our data set. So basically if you see this word the as a center, then previous to this the word there is not any words. So for this case there will be only two training samples. Okay. And for a quick you will get a 3 training samples, and like a fox for a brown also you will get 4. Okay. Now we will see how we are going to train our skip gram model. So basically here our task is to predict the predict each context word given a target word. Okay. And as I told you earlier, all these words means we have to represent these words into vectors. Okay. Means we cannot directly pass the word to our neural network. Okay. So basically here we are going to our first step is to convert our target word into one hot encoding vector, and it should have the dimension as same as the dimension of vocabulary. Okay. And here we have output layer which have the all the words that are present in our vocabulary. So here also in our output layer we will having similar number of words. Okay. But now you will ask how we are going to learn these embeddings for the words. So basically here we have initialized two matrices with randomly we have initialized this. This matrix W is known as embedding matrix, and this W dash matrix is known as a context matrix. Okay. And in this model we have one hidden layer which contains the n dimension. It is an n-dimensional vector, and n is representing the size of your vector for your every word. Means if you want to encode your embed your word into 100 values, then this n should be your 100. Okay, means
Sir, sorry to interrupt.
okay.
So we are converting the words into numbers here. Which method we will be following, sir? The methods which you have discussed previously. One code one hot encoding. The similar methods are used to convert the word into vectors, sir.
No. Actually, this is our means this is a word to vec model, and how this will create. Means I will tell you in the next slide, but how it is going to encode your words into a vectors. Okay. In the next slide you will get to know about this, but basically your input to a neural net, this neural network is the one hot encoded form of your target word. Okay, what we have basically created in our training data, we have created this target and context pairs, right? These first words are representing our target words, and this quick brown, the second words are representing our context words. Okay, and from this matrix we are going to learn the embeddings. Means these values are going to update when you train this network, and this will give us that particular kind word embeddings. Okay, I will discuss this part in this slide. Consider your training pair is as a brown and fox. Means your target word is a fox. Okay, and your context word is your target word is brown and your context word is fox. Okay? But you have to feed this brown word to your neural network. So basically in our dictionary, first we will convert this brown word into a one hot encoding format. Okay, so the dimension of this vector is v cross 1. Okay, so v is representing the number of unique words present in your dictionary. Okay, then this W matrix is come, and we are going to the dimension of this W matrix is v number of rows and n number of columns. Okay, and this matrix is randomly initialized. Means it has some random values, but when you multiply this v cross 1 vector with this matrix, you are going to get a vector of size 1 cross n value, 1 cross n dimension. Means here you will have the n values basically which are presented in this particular row. Means basically it is giving this complete row here. Okay, and here as I told, the dimension of a W are v cross n. Means v is the number of as I told here, this v and this v are the same. Means for every row of these matrix are representing our every word. Okay, in our vocabulary with dimension of n. Okay, actually here for the multiplication you have to take the transpose of this input vector. Means basically here as you can see these values, these are the number of rows, okay, and it has only one column, so I have put these as v cross 1. But to get this vector, you have to multiply with these vectors transpose, so that you will get 1 cross n. Okay, and then we have another kind of matrix, which is w dash. Okay, actually it is not a transpose of your this W matrix. It is also randomly initialized. Okay, and it contains n number of rows and v number of columns. Okay, and again we have to multiply this hidden vector to this W dash matrix, and we will get one vector with a dimension of yeah, again here we will get the v cross 1. Sorry, here I have put the transpose of this size, but here we will get the v cross 1 value. Means here basically our task is to get the one value here at the index of j, where actually the j index is corresponding to the fox, as we have given the training pair as a brown and fox. So basically here we are giving our target word as a brown to our network, and here our aim is to get one value at the index of a fox. Okay, but as these matrices are randomly initialized at a initial kind of at initial number of epochs, you will be getting some random values, but our task is to apply the softmax. Means here we have to in our output layer we have the softmax activation function, and we should get one value at this index. Okay, so and in initial epoch it will not give 1 year, it will give some random values. Okay, but we have to do the back propagation, and we have to update the w dash values in the w dash, and we have to again update the values in w. Okay, and we have to do this this back forward propagation and back propagation on our complete data set on several epochs. Then only we will get the this embedding matrix, and then we can say that this matrix is our best embedding for our words as far as our data set is concerned. Okay, so I hope your doubt is clear. Okay, so we will see the next kind of model, which is a back of word model. It is a similar kind of model only, but basically here the difference is that here we are predicting that missing values, that blank values, and we are providing our network some context values. Okay, so here we are again our first task is to convert this every context word into a one hot representation of their one hot representation, and we multiply with these w vectors. Okay, so basically if we have the window size as 2, we will get the four words here, and when we multiply with this w matrix, we will get the 4 vectors. But here we have to average that 4 vectors, and then only we will get the one vector with the same dimension as 1 cross n. Okay, and then we will multiply this hidden vector with our w dash vectors, and here our output vector we will get that output vector. And here our aim is to get one value at an index of brown. Okay, So basically here again we are as we are using the softmax function here, activation function here, and we will do the back propagation to update these parameters of w and w dash. Okay, but basically now you will ask why we are using two kind of vectors. Okay, so basically this kind of this context words you can skip this matrix, means actually this both with these both matrix will capture the similar kind of will capture the similar kind of patterns in it from your word. Okay, so you can mainly depend on this kind of matrix only. You can skip this part also. But you when you see our output layer is of in our output layer we are using softmax function. Okay, now in our consider our data set is our data set contains 10,000 words, then it will be very computationally expensive operation to do the to find the summation on your complete data set. Means if you see your softmax function, okay, it is kind of this here on the numerator we have the exponential term of u0t into vc. Actually this is u0 is a vector which is corresponding to your context word, and vc is a vector corresponding to your center word. Okay, that we have seen here. What we have seen that we have to do the multiplication of this vector with this vector. Okay, so our probability to get the probability to convert, means all these values into a probability, we have to do this much of computation. So if you have 10,000 words, then for every training sample you have to do this kind of work, which is very heavy. Okay, so how this drawback is going to we are going to solve, we will see in the later slides. Okay, but here I would like I have to share the object, what is the objective function of our word-to-vec model. Okay, so basically you have understood that this is our softmax function, and we have to find the likelihood, means we have to find the probability of words that are coming in the window of fixed size given our that particular word. Okay, and this theta is our neural network parameter, some different parameters such as maybe the size of vector or learning rate, or maybe these kind of things. And the loss function or the cost function here we can simply represent it as the -1/t into log of like our likelihood. Okay, so here we are so it is basically similar, it is similar to your cross entropy function. Okay, so now we have understood that how we are going to train a neural network, and how we are getting the embeddings for our words. Yes, actually I forgot one point. Here I told you that I referred this task as a fake task, because our task is not to develop a neural network that can accurately predict the this target word or the context word. Our main aim is to find these metrics, these updated metrics, so that we can use this kind of these embeddings in our different applications. Okay, so if you are getting the low accuracy or low accuracy in your this task, it does not affect, means if you are getting 70-80%, then it is fine. You can means say that whatever you are getting in this matrix are good. Means they are good representation for your words in your presented in your data set. Okay, but how we are going to evaluate our models? Okay, there are two kind of actually there are two kind of evaluation methods. One is intrinsic evaluation, one is extrinsic evaluation. Okay, so basically analogies comes under the intrinsic evaluation of our word embeddings. Okay, analogies means how A is associated to B, and we are going to find the what is similar kind of relationship between C and that particular unknown values. Okay, so basically here you can see that we are mapping here the country and its capital. Okay, so you know the capital of China is Beijing, and you want to find what is the capital of Germany. Then how these word embeddings are going to help you, that we will see. And if you are getting the proper answer, like you should here get the Berlin as your answer, then you can if you are getting that Berlin, then you can say that your embeddings are properly calculated. Okay, so basically to calculate the this unknown value, we can use this formula. Means we know that we can apply the means addition and subtraction operations on vectors. Okay, and actually these all vectors corresponding to all these words are with same dimension. Okay, then to find these unknown value, we can subtract the the vector of Germany with vector of China, and then we can add the vector of this Beijing, so that we will get these vectors, and then we will compare these vectors in our data set, and it should associate it with our Berlin word. Okay, if it is, then we are good to go. Means we can good to use that word embeddings further. Okay, so not only this kind of relation, means analogies, it is going to find, means it can find any kind of analogies. Means here you can map the degrees, means superlative degree, comparative degree in your in our 2D space also from our word embeddings. Here I have put one example of this. A drive is associated with means the person and his task is associated here. The driver has the task to drive that particular vehicle, or the student is learning, means student is associated to learning, and here teacher is associated to teaching, like this. Okay. So actually we don't have to install this any specific libraries here to find these analogies. Basically what we are getting from these matrices that we are evaluating that matrices only. Okay, there is no need of any other thing. Okay, that matrix we is going to actually means we have to evaluate that matrix only. So basically this is one kind of method to evaluate and see how good it is.
Sorry to interrupt. So here Berlin will be given depending upon where we are getting 1, right, sir?
One.
Means for example, the vector is represented as zeros and ones.
Okay.
In order to get the capital as a Berlin, we need to see where we are getting the value 1 after this equation. Germany minus China plus Beijing is equal to Berlin. That is what happening here, the equation which we are solving.
Yes, actually you don't have, means actually these values are represented into 2D space, but this can be a n-dimensional vector for associated for every word. Okay, so basically means
Yes, my doubt is how exactly we will be coming with Berlin as an answer. If not, we will go back for back propagation, which you discussed in the earlier slide, in order to update our model. How exactly the Berlin will be coming here?
Okay.
What are the parameters we will be taking? That is my doubt, sir.
Okay. So consider you have you have got that W vector. Okay, and you in your data set you have these 3 words. Okay, and then from that matrix you can find the vector for China, right? You can find the vector where means at that particular index you can find the vector for Beijing and for the Germany, but in your means, and similarly at in your data set the Berlin should be present. Okay, and means if you see these 2 are the countries. Okay, so we have to subtract the whatever these subtract these two contents, and we have to add the capital so that we will get the capital of this particular country. Okay, means you can consider like this: we are subtracting the content of country from this vector, and we are adding the capital the content of capital in this vector. Okay, so what you will get the some particular vector, okay, here by performing these operations. And if this vector is similarly to what is the vector for Berlin in your data set, you can find that using cosine similarity. Okay, if the angle between these two vectors are nearly 0, then you can say that yes, these means means you are going in the right direction. Like this we are going to evaluate our models. Okay, are you clear?
Yes, sir. Got it, sir. Got it, sir. Thank you.
Okay. So actually I have told earlier that as big as your dictionary data set or dictionary size, then your the computational cost of the performing softmax function is more. Okay, so how you are going to reduce this computation cost? Okay, so there are 2 types of techniques here. One is negative sampling and second is hierarchical softmax classifier that we are going to see. In the negative here our aim is means whatever we have studied the softmax function, but here we have to modify our objective function so that it will reduce our computation cost. Okay, so consider you can consider here one pair from your data set, which is Fox and Quick. As Fox is your center word and Quick is your context word. Okay, and you have to assign means you have to find the probability of appearing this kind of pair in your data set. Means if it is appearing in your data set, you have to give this pair as a label 1, but to do the back propagation thing, we have to randomly sample some of the pairs that are negative in the sense that are not present in our data set, or in data set that should not present. Means the fox and you should means it will not come in the that particular window, like fox and dinner, fox and guitar, fox and chair, fox and table. This kind of pairs will not never occur in your data set. Okay, so basically here we are converting our softmax task into a sigmoid task, whether this kind of pairs are appearing in your data set or not. If it is appearing means it is present in your data set, then we can give the label as 1, otherwise the label would be 0. So here we have to slightly modify our objective function. So here for our positive sample, we can find the sigmoid of our this product of these two vectors, and for the negative samples, basically we have to first we have to sample some pairs from our entire data set, and then we have to get this value. Okay, and this will be our cost function for the negative sampling. And for this case here you can take as a five negative samples, means that your k value is 5. Okay. And actually this is your one of the hyperparameter, and you can change this to any value. Okay, so here I have considered as k, and you have to means you have to do this perform this loss function on your entire data set, and you have to calculate your loss, and again you can do the back propagation and update your words. So here we are avoiding to find that the sum of 10,000 words. Okay. Next topic is hierarchical softmax classifier, and it is also one of the method to reduce our computational cost of in our original model. Okay, so here basically we are trying to divide our entire vocabulary into a tree-like structure. Okay, so to divide this tree-like structure, we have to do this Huffman encoding. Okay, and to find the word where it lies, we have to again we can find the probability. It means we have let's consider you have to find the word as W2, and it is present in the left tree of this your main tree. Okay, in the left subtree it is present. Okay, then at this node you have to find the probability whether it is present in this subtree or it is present in this subtree. Then here you will get the higher probability as it is present is here present this side. Okay, then you will move down the this tree, and again you have to calculate the probability at this point, and by doing this operation till you reach, you have to do this operation till you reach your word, and these words are located at the leaf nodes, and in this manner we can reduce our O of n complexity to O of log n base 2. Okay. I hope this part is clear, but now there are some of the limitations of word-to-vec model. Okay, so we have seen that it is only relies on your local information. Okay, means basically you have to take the window size with respect to your center word, and you have to generate those kind of pairs. Okay, that means the semantic that you are going to learn for the center words are only dependent on your surrounding words only, and means this kind of sublinear relationship are actually it is explicitly defined, okay, in this model. But now we will see the different architecture. Its name is Glow architecture. It is developed by some of the peoples at Stanford. Okay, actually this model is unsupervised learning algorithm. Okay, so whatever we have studied, means we have seen in word-to-vec model, actually it is a supervised model. Means it was creating the labels from the unlabeled data. Okay, and then it is going to evaluate, means calculating your embeddings. But in this GLOW model, it is a unsupervised learning. It is unsupervised learning algorithm. Okay, and to find the word embeddings, here we have to create a one matrix which name is a co-occurrence matrix, and it should have the size of V cross V, and again here V is representing the size of your dictionary. Okay, and here xi, the value is corresponding to this xij value, is it denotes how many times the word I has occurred, co-occurred with word j. Means I have taken this same sentence. The cat sat on the mat. So if you see the word here in this sentence, then it is co-occurred with cat, on, and mat. Actually here the we are considering only one word at a previous one word and next one word only. Okay, so here you can see how many times the cat has appeared near to the word. Okay, one time the sat is not appeared, and actually you will get this diagonal as a 0 always. Okay, on is appeared once, mat is also appeared as once. So so that in this manner we can calculate this co-occurrence matrix. So basically it is going to capture your not only your local statistics, but also it is going to capture your global statistics also. And it is means it is depends on your word-to-word co-occurrence statistics from your corpus data. Okay. So now we will see how we are going to get the matrix, to get the matrix from our this co-occurrence, the X matrix. Okay. So here you can see one table. Here we in the first row we are representing the probabilities of occurrence of a K word given ice word. Okay, and if it is a K word as a solid, then we can see that what is the probability. Okay, if it is K as a gas, then what is the probability? K as a water, what is the probability? Okay, and your second word is a steam. Okay, and again you have given the same kind of K words, and you have given the same you have given the probability of the occurrence of that K word given stream is present. Okay, but when you take the means when you divide this probability with this probability, then you should get a high probability here. Means for ice should be a solid. Okay, but steam is not a solid. So here we are the occurrence of this means this probability should be higher than this probability. Okay, so it should be greater than 1. Okay, and similarly for the gas, it is relevant to more relevant to the steam rather than ice. So it should be very smaller than 1. And for the neutral words, we are getting the value near to 1. Okay, so this is our main this is the main idea behind the GLOW model. Okay, but we have to map these probabilities to a function so that we can means we can find the relation between our word embeddings and these probabilities. Okay, so how we are going to do this, that we will see here. Here you can see one function with three vectors, and you have to map with scalar values. Then can you suggest what should be our f? Because here our input for our f is our vectors with some n dimension, and but here the output should be your a scalar quantity. Okay, so can you suggest some function related, means what kind of function can we use here? So any idea? You can share it in chat window. Okay, sigmoid. So yeah, but sigmoid, but we have to find the relationship between these, means how these three vectors are going to use in sigmoid, that means, or what are the other possibilities that we can see, means we can use here that we are going to see. So basically again, these all are words, and we can do addition and multiplication on these vectors. We can find means instead of working on a three variables, we can reduce it to two variables, because to do optimization problem on three variables is more complex task rather than into two variables. And if we are taking the difference between these two kind of words, then we are getting same kind of results. So again, here we can reduce that thing. Okay, so instead of representing our function like this, we can represent our function like this, that wi minus wj transpose into uk is proportional to the probability of ik divided by probability of jk. Okay, so now what is this f? What can be this f? So we have to replace with some means actually we are seeing this as some function only, means it is we have to represent it in some mathematical model. Okay, so we have to see that what can be the choice for our f. So f, we have to select f such a function that it should have the property of a homomorphism property between the additive and multiplicative groups. Okay, so basically here we are dividing, means here we are splitting our equation. Okay, we can distribute these things, and we can write this thing as individual multiplication rather than doing subtraction and then multiplication. And then we have to as this we have minus sign, we have to we can write this as a ratio of two values. Okay, so here it is first value, which is the numerator, and this is the second value, which should present in your denominator. So here the function, the proper choice of function may be the exponential function. So you can perform this kind of operations in your exponential, and I will and you will get the scalar values as your output. Okay, so here remember one thing, we cannot directly equate this numerator value with our numerator of this pik and the denominator to this pjk. It is a means it means it is relation, means the ratio of the LHS is proportional to the ratio of RHS. It is not a similar values. Okay, and as we see, there is one function, exponential function, that possesses the property of homomorphism. So we can represent our word this function in this format, and if we take the log in both sides, then we will get the product of these two vectors. And from starting, we are looking at the dot product of two vectors, and how I mean, these are going to give us the similarity between these two vectors. And here now we will get the this term, log of xik minus log of xi. Remember this xik is denotes the number of times the word I is co-occurred with the number of word k. Okay, and here our k is our context word. Okay, so basically we have to perform the operation based on our k vector, k, or a k word, you can say. And if you see, this is dependent on k, this is dependent on k, but this value is independent on k. So we can represent this with our bias term. And this is how the GLOW architecture is. The idea of the GLOW architecture is that the dot product of two vectors plus some constant value will going to give you the log of how these words are co-occurred in your corpus or in your data set. Okay, and now we can we can find the error by doing the mean square operation on our equation. So basically this is our cost function in our GLOW model. So remember, if you are this is the co-occurrence vector that we have calculated initially for our sentence. Okay, and here you can see there are many such elements in this matrix are 0. So basically when 0 appears here, then this becomes minus infinity, and your error will be infinity, and this is not desirable case. Okay, so how can you avoid this case? See the scenario here. So this scenario, there is one option of Laplacian smoothing, that we can add 1 here, 1 plus xij. But the GLOW authors have used a different approach to eliminate this problem, this kind of problem, and with the help of this function f of xij. And this f of xij actually helps them to reduce the problem of extremely common word pairs. Means some pairs like the, and, on, this kind of words are more frequently occur in our data sets rather than some values like apple, fruit, mat, cat, sat. Okay, so so this kind that kind of problem they are trying to eliminate with the help of this new function, and this new function is the weighted sum of our mean square errors. Okay, so we have to first we will see what is this f of xij. Okay, so here they have given one formula, like if xij is small than x of max, then we have to use this kind of value. Okay, or otherwise we can replace this one as a value. Okay, so consider here you are getting a 0. Okay, so basically here again automatically you will get 0 value. So this complete term will be eliminated from your data set, means sorry, from your cost function, correct? So this is how this weighting sum is useful here. So now we will summarize the these two models. What are the positive points in word-to-vec model, and positive and negative points in word-to-vec model, and yes. So if you see that it is a word-to-vec model, it is a supervised model, means it is transform your unlabeled raw corpus or a data set into a labeled data. Okay, and it requires less amount of memory, and it is going to find the embeddings with sublinear relationships explicitly, okay, not implicitly. It will find, but the drawback here of this word-to-vec model is that it is very computationally expensive. That we have seen the softmax function, how it means how much it is expensive. Okay, and the second drawback, you can say that it is giving you only local information, okay, within that particular window, not in it is not giving you the global statistics. But if you see the glow model, then you can see that these word vectors are calculated from your co-occurrence matrix, and it is basically gives you the global as well as the local statistics, and it enforces the word vectors to capture the sublinear relationship between your in your vector space. Okay, and if you see it is so that if you remember that table that we have seen, ice team, it is more practically it adds more practical meaning to our model. Okay, but the drawback here is to store that huge co-occurrence matrix in a memory is one main drawback. Okay, and the second drawback, if you change some of the hyperparameters, then we have to again do the complete procedure. Okay, but here I want to share one important point with you guys, that these two the two drawbacks of these models, that means that it is not solve the kind of problem that we are going to see here. How it is going to learn some words that are not occurred in your vocabulary, means if you have the vocabulary of 10,000 words, and in the next day if the new word come, okay, in but how you are going to find that the word embedding for that vector? It is these models are not not have that privilege to find the out of word vocabulary representation for out of word vocabularies, and sometimes it finds it difficult to find the encoding of opposite pairs such as bad or good. Okay, so maybe means here suppose I have to give one review on restaurant, means bad review on the restaurant. Maybe I can say like this, I did not means the food was very bad, the quality of food was bad, but I can say that the food was not good. So the this so that time when good and also bad means contributing this means the same kind of meaning, means the negative feedback that these two models are not able to capture that things. Okay, so what is the next model we have? It is a fast text. Okay, it is a library developed in C++. Actually, this library is developed by Facebook team to learn the efficient word representation and to do the sentence classification. And actually, it supports the multi-processing during the training, and it have both kind of supervised as well as unsupervised representation of your words. And actually, if you see the implementation of this fast text, then we can say that it is extension of our word-to-vec model. Okay. So in word-to-vec model, if we see the skipgram model, what it does, it predicts your it predicts means we are feeding a center word to our model, and it is going to predict the context words. Okay, so basically it is working on your words part, but fast text, how it is different from word to vec. Actually it represents your word into n grams characters. So n grams means you have a word like machine. Okay, and suppose here I have chosen n as a 3, means I have to split this word into a 3 trigram, okay, or 3 gram, we say in this in NLP for this. And means basically here we try to divide our this word into a small kind of set of characters. Okay, so here the opening and closing brackets are represented by your angle brackets, and here as we have taken n equal to 3, then we can put the initial two characters, then we can move by one and we can have the MAC as our next sample in our training data. So in this way it is going to represent your words in means it is going to represent your data in your training set. Okay, and this representation is going to help us because actually if you see what are the advantages, then you can realize that it works well on the rare words. And we have seen the drawback of word-to-vec model that for the out-of-word dictionary words, it is not means it cannot capture the representation for that word, but fast text model is going to capture it will capture that representation for the unknown words also. So this is how means n grams are implemented to improve our word-to-vec model to find this kind of embeddings. Okay, so basically till now we have seen how we are going to represent our words into vectors, but if I say that we can represent our individual document or a sentence into one vector, then how we are going to proceed? Actually here we are going to see the doc2vec model, which is which is a extension of a word-to-vec model only with some little modifications. Here we are going to add another matrix which is known as paragraph matrix. Okay, and the similar kind of process here we are going to follow to find the vectors for your data. Find the vectors for your document, and instead of finding the vectors for each and every word in your data set, you can directly find the vectors for your document, and you can develop one other model that will classify your individual document into sentiments. Means instead of doing splitting vector tokenizing this thing, the complete document, we can directly go for this kind of model. So here also we have two kind of models. One is distributed memory version of paragraph vector, which is based on our continuous bag of word model. Here it is the architecture of this model. Okay, as we know, for a continuous bag of word model, we have to pass the several context to our input, and it will predict a one center as our output. Okay. So at a time of a training, we can add this paragraph matrix, and this, with the help of paragraph ID, we can get one vector from this matrix, which is the representation for that. And again, we have to do the average, or maybe you can do concatenation, and you will have the classifier at this end. Okay, and this, in the same manner, you can train this matrix also. And previously in word2vec, we were updating our this W matrix with the help of backpropagation. Okay, so, and this is the second architecture presented in our doc2vec. It is extension of skipgram model, where we only give our document vector to our model, and it based on the context word, means based on the words are presented in our document, it will try to update the values here. Okay, this is it from doc2. This is means from after this we will see some questions that will help us to get a more clarity about this topic. So here I will read the question, and you can give the answer in the comment chat window. Okay, so suppose we have learned the word embeddings for a vocabulary of 10,000 words, then the embedding vector should be size of 10,000 word dimension, so to capture the full range of variation and the meaning from this word. Is this sentence is true or false? What do you think about this sentence? Do we need this 10-dimensional vector to capture the full range variations? You can type your answer in window. Okay, false. Okay, yes. Okay. Yes, as yes, the correct answer for this question is false. As we see, we can do in the less dimension also to capture the features of each word. Okay, the next question we will see now. You have to find the proper equation for the relationship between this word embeddings. Here means which of the following equation do you think should hold good for our word embedding evaluations? Okay, so here the multiple options are correct. So can you means find those equations? How we can say that LHS, when we can say that LHS vector is equivalent to RHS vector. Okay. A and D. Okay. Okay, here some people are typing A and D. Okay, so can you see the options again? And actually, D option is not correct. A and C is correct. Yes. So basically, the means here the difference between means here you will get the here boy minus girl, and it is a similar kind of pattern you will see in brother and sister. Okay, and if you do a boy minus brother, then you will get the similar kind of vector in girl minus sister. Okay, but if you see this D part, then these brother and sister are more means these boy and girls are more specific. Okay, so no, sorry, these brother and sister are more specific than boy and girl. So it may give the negative of this part. Okay, so now we will see our next question. The next question is that when learning word embeddings, we create an artificial task of estimating probability of a target given context. It is okay that we do poorly on this artificial task, and the more important byproduct of this task is that we learn a useful set of word embeddings. Is this sentence is correct or not? Okay, means actually this sentence is trying to say that the whatever we are going to perform, whatever we have to perform in each artificial task is not mattering how the word embeddings we are getting. Okay. Okay, yes, the correct answer is true, that I talked means I shared that the fake task we are going to perform with new in skipgram and continuous bag of model, bag of word model, and our main aim is to find that particular W matrix to get the proper encoding. Okay, but okay, now we will go to next question. Here you can see the cost function for your glow. Okay, and your glow contains the 10,000 words in your vocabulary, and each word is represented in the 5-dimensional words. So you have to find which of the following sentences are correct, and there are multiple options are correct. Okay, so I will read this option. The weighting function f must satisfy f of 0 equal to 0. Okay. Xij is the number of times word j appears in the context of word I. And third option is theta I and ej should be initialized randomly at the beginning, and theta I and ej should initialize at 0. So what you think in glow model, what we are what we as far as this glow model is concerned, what are the options are correct? Can you put in chat window? Okay, yes, we have seen that co-occurrence matrix X represent the number of times the word appears in the context of word I, so it is correct. And the second option is we have to means we are initializing this theta I and ej are okay, theta and ej as randomly, and with the help of backpropagation we are going to update those weights. Okay, so this is our last question. here in our word-to-vec model, we have again the 10,000 vocabulary size, and each word represents the 500 dimension word embedding. And here also the multiple options are correct. So can you guess, means can you find which options are correct here? Oh, actually C and D. Okay. Can you read the question again here? I think it is mentioned that the word embeddings has a size of 500 dimension. Okay. So B, C, okay. So I will give the answer. Actually, B and C is correct. Okay. So as mentioned in the question that 500 dimensional vectors are present. So each these vectors will be having the dimension as 500, and these are going to train with Adam or gradient descent approach. Okay. So now we will see one test case here in Python. Okay, I will share my notebook. Okay, can you see the notebook? So you can type in chat window. Can you able to see my notebook? Okay, so here in the notebook we are trying to build one model. It is means basically our aim is to do the sentiment analysis here on Twitter USA Airlines. Okay, means we have some tweets for the means commented on US airline, and we have to find it is a positive feedback or in negative feedback, or the tweet is in normal, means in neutral. Okay.
Sir,
So
will we address bias here, sir?
What's that?
So we are making the sentiment analysis, right?
Yes.
There may be some institutes which may hire some people, and they may promote themselves to have maximum number of positive when we compare to the negative feedbacks, which will lead to the bias state. Will we address such kind of situations here?
Yes. Here we have taken this data set from a Kaggle, and actually this data set is imbalanced form. Okay, means here we have the a negative feedbacks are more than a neutral or the positive feedbacks, that we will see later how we are going to address that as we go in our this notebook. And here we are going to build one LSTM model with our embedding layers, and at output we will be having one sigmoid function that will give whether this sentiment is positive or means it is sentence is positive or negative. Okay, so basically first we will see what is the data set here. The data set, you can see the this second column is giving us the label, whether it is neutral, positive, negative. Okay, and this is a tweet ID, and we have to find the tweets are presented in this column. Okay, so in the text column of the CSV file, we are having the tweets for this US airline company. Okay, So we will explore this data set. Here total we will means in our data set total we have 14,614 number of tweets. Okay, and from that we are going to use only 14,000. Okay, actually we can use here all the things, but some we are kept for our evaluation of a model. Okay, so here first we will take the reviews and the labels from our data set text column and airline sentiment column, and if we randomly pick one tweet, and we can see that here that complete tweet here. So here if you notice that part, then here the airline the at the rate and airline names is coming. Okay, and it is similar in all the tweets. You can notice this part. Okay, actually this part is not required to classify this sentence into whether it is a positive or negative. So we have to eliminate this kind of things from our tweets. Okay, means we have to do some pre-processing on our on this data set, and with the and if you see how these are distributed, means the how many number of values are of a negative belongs to negative class, it is 8,679, where the neutral and the positive tweets are very less. Okay, so we can see that it is a very imbalanced data. So, and here we have total 3 number of classes. Okay, but here we will try to slightly change our these labels. Means we will convert this into a binary classification task. Okay, so in that task we will consider a negative as a one class and neutral and a positive as a one class as a non-negative. Okay, and for data pre-processing, we have seen that we have to remove that at the rate character, and in some of the tweets there might be the HTTP is present. Okay, that also we have to remove. So basically with help of this for loop we are going to remove. But what we are doing in this for loop, first we are splitting our means in this list we have all the reviews. Okay, sentences in the sentence form. Then we are first we are splitting with the help of this function, and we will getting, means it will be splitted on the white space, means where it is space, then it will split, and we will get the year one list containing words, and we will search whether it contains the at the rate or HTTP or any digit. Then we are not going to include in our data. Okay, and we are simply ignoring them. Okay, and this is we are going to perform on our complete data set. Okay, means or 14,000 sentences, and if you see unique number of words in our entire corpus, then it is giving us the 1626 number of unique words are present. Okay, and here we can see the tokenize for the first three. Okay, first two tokenized words. Okay, and then we are going to encode our labels. As I said, we have the three types of classes, but we are going to encode these labels into binary so that we can do a binary classification problem. Means for the negative class we are assigning the label as a 0, but for the neutral and the positive class we are assigning the value as a 1. Okay, And you may say, we see that in our data set, the not every sentence will have the same size of words in our data set. Means in some tweet you can see that the number of words may be very less, 10, 5 number of words may be there, and some of the tweets we will have more number of words. So basically here we can write one function that if our if the tweet contains less than 30 words, then we can pad zeros, okay, at initial. Okay, and if our word is more than particular sequence of length, then we can truncate to that sequence length. Okay, so basically here the sequence length we have taken as a 30. Okay, means if it is less than 30, then it will pad and make 30, and if it is greater than 30, then it will reduce it to 30. Okay, and this is how it looks like when the sentence is less than 30, then we are going to append the zeros. Okay, so here our first task is to split our complete data set into train, validation, and test part. Okay, so here we have considered only 14,000 tweets in our data set, and we have taken the split as a 0.8%, means 0.8% values we have in our training data, and remaining number of values we have split it into a validation data and a test data. Okay, so here we can see the dimension for each. Okay, so so basically this LSTM model we are going to develop in using PyTorch framework. Okay, so here whatever we have the values, it is present in numpy vectors. Okay, so basically here with the help of this tensor dataset, we are converting this numpy to tensor values, and with the help of a batch loader we will pass the batches to our model, and it will train our model. So here basically we are performing a mini batch gradient descent type of algorithm to update our weights. Okay, so here we can see if we do the perform one iteration on our train loader, then we will get this kind of samples. Sample means input and it corresponding labels. Okay, here we have taken the batch size is 50. So in every batch we will have the 50 number of tweets or sentences. Okay, and now we have to build network that we will see the architecture. Here I have that image. So first we have to here first we have embedding layer, and then we have LSTM layer, and then this LSTM layer is fully connected, and we have one neuron in output which having the sigmoid activation, and which is giving us a binary output. Okay, so this kind of model we are going to implement. Okay, so here I am doing this on a CPU. So here training we have to do, I am doing in a CPU. So here one command that is torch.cuda, which is available in PyTorch. So if you want to do in GPU, then you have to convert those tensors into .cuda format, so that it will process by the GPUs. Okay, first we will create this class for our RN means LSTM model. Okay, here we will assigning these parameters. Okay, then here we are using inbuilt embedding layer, which is inbuilt in PyTorch. So basically what it does here, it create that particular size of matrix of that W matrix with a size of n cross v. Okay, and it will randomly initialize. Basically, if when you use this function, means there is one parameter here. I will show you in the documentation. Here you have this weight kind of parameter to this function. There you can pass your pre-trained word embeddings, or if you don't have the pre-trained word embeddings, you can means it will learn through our backpropagation step only, and it will find the embeddings for our words. Okay, but when to use this and when to not use pre-trained model. It is similar kind of, means you can consider it is as a transfer learning kind of thing, where if your data set is too small and you don't have much unique words in your data set, then you can go for pre-trained GLOW or word-to-vec model that we have seen earlier. Actually, it is trained on Wikipedia dataset, and it has a very good embeddings that we have seen already. And if you don't have means if you have huge amount of data, then instead of going for this pre-train, you can directly means you can keep this as an and you will means you will get your own embeddings. Okay, so here in this case I am not using any pre-trained model. Okay, sorry, any pre-trained word embeddings. I am training these embeddings from scratch. And then one dropout layer is used here, and then these neurons presented in a LSTM layer, which will be fully connected with our output neurons, and it will have the sigmoid. So if we see the architecture of our this model, then it looks like this. Here in the embedding, we have seen that our data set contains this many number of unique words, and we are going to represent each word into 200 in 200 dimension space. Okay, and in LSTM we are going to pass these 200 values, and we will be having 128 number of neurons in this LSTM layer. Okay, and this 128 is connected to our one neuron. Okay, this input is 128 and output is 1, which is our output neuron, and we are using the activation soft sigmoid on that output layer. Okay, then here as we are performing a binary classification model, we have to use binary cross entropy function, and here we are using Adam optimizer to update our parameters. And now we will do the training of our model. So here I have set the epochs as a 10. Okay, and if you have a GPU, then you have to run this command. Okay, and it will run your neural network on a GPU. Means it will use the GPU. Otherwise, it will process in your CPU normally. This function gives means it gives that we have to train our model. Okay, means when we call this function, then it goes in the training mode with and it will update the values, means it will calculate the loss and it will do the back propagation and it will update the words using whatever optimizer that we are going to use. Okay, and for the here in the we have written the for loop for the every epoch, and we are going in every epoch we have to go from our complete training data set. So it will, for this for loop is to access each batches in our training data set. So for first it will convert into a and say if you are GPU, that same thing we have to do here. It will convert into a CUDA format, then it will, then only it can run on a GPU. Okay, otherwise it will consume your CPU computation. I mean it will work on the CPU only. Okay, so basically here we are passing our inputs here for to our network, and we will get some output, and these output are we are going to pass in our criteria. This is criteria means our loss function. Loss function here is the binary cross entropy, and then it will calculate it will do the back propagation step here, and it will in this optimizer dot step function it will perform the update. Okay, so we will see how it means here for every epoch I am printing here the training loss and the validation loss, and here you can see the validation loss is decreasing here, and but here at initial some epochs, but here then the validation loss is increasing. Okay, but if you see here in the training loss is continuously decreasing in our every epoch. Okay, and after doing this means here we are getting some not means here we are not getting much good loss as compared to our training loss. Means validation loss is more. So one of the drawback, I mean, so one of the reason why we are getting is that we are not using a pre-trained word embeddings, right? So here if we use that pre-trained models, then we will get more accurately classified our tweets. Okay, and
so we can consider pre-trained model as an hyperparameter, sir.
No, actually no. If you see when you use a transfer learning model in CNN, then you will slightly get a good accuracy, right? Means what we are doing in a transfer learning, we are using that pre-trained weights, and we are training only initial few layers and last layer. Okay, last few layers. So that's the only we are going to update, but basically the middle layers are we are taking the means we are using that pre-trained features. So here also to use that pre-trained features, we can use that pre-trained model that is available. You can use that word2vec or a glow which perform which actually calculated embeddings on Wikipedia dataset, which is a very huge dataset, and it contains means millions of unique words. Okay, so here if you see our accuracy is not, means it is good, but it is it can be a better than this. Okay, so after training the model, we can use we can use to predict the this new tweets. Okay, if you consider means if you have this kind of tweets which have the negative, then again we have means to pass and to predict the what it means to find the sentiment of this tweet, we have to again process do the pre-processing on this sentence. We have to remove this at the rate and these question marks and all these HTTP things, and then we have to pad it to a size of 30 that we have done in our at a time of training, and then we can pass it to our network and it will predict it will give output at 0 or 1. So means basically it will give the output as a probability here, and we can put the threshold as 0.5, and we can see that this function is having the negative review. Okay, when you pass to our model, it is giving very less value, and which is less than 0.5, then we can say that it is a negative review. Or and in this kind in this type of tweets, it is giving the almost values near to 1, which is means we can say that it is more above thresholds, and we can say that it is a non-negative type of review. Okay, I think yes, this is yes. So do you have any doubt regarding this?
Hello everyone. Yeah, so maybe now it is the time where you can ask your doubts, any query regarding the session. Maybe if you haven't followed any topic or any particular information that you would like to ask to Samir, it is the time. Okay, if there are no doubts, could you guys please respond with no, and then we can proceed further. If there are any doubts, you can unmute yourself and ask your doubts. Okay. Okay. Okay, fine. If there are no doubts, then let me thank you, Samir. First of all, thank you so much for such an amazing presentation on the vector space models. And people have been talking a lot about the feedback link while the session was on. I'll humbly request you guys to focus on the knowledge being shared in the session instead of being worried about the feedback link, recordings, and other stuffs. Okay, because if you lose the focus while the session is on, it defies the whole purpose of keeping this live training session. Okay. And Vishal is asking, can you provide the Collab link, sir? Okay, let me get back to you on that, Vishal. Okay, so let's talk about the feedback, because you have been talking a lot about the feedback while the session was on. So before we share any link for the feedback, let's hear from you guys what you guys have to say about the session. Was it useful? Did it help you guys somewhere? You can unmute yourself and talk few words about the session. If you're uncomfortable speaking, then you can put down your review in the chat window. Whatever is comfortable with you guys. Anyone? Okay. Prince is saying it was informative and a very good session. Anybody would like to unmute himself or herself? I got to know a lot about this new thing. Okay. Vector space model is not something new, Prince. It is like quite a buzzword in the IT industry, and everybody should be knowing about the vector space model because there are lots of information that is in unstructured, that lies in the unstructured data or in the form of unstructured data. So vector space model is something one should be knowing pretty much. Okay, being in the first year, I'm not having much knowledge about it. That's absolutely all right. You have taken your first step towards machine learning. So I guess that's pretty good. And we'll be conducting a lot more live training sessions, Prince, in future. Make sure that you attend all of them. And you can ask as many doubts as possible because speaker would be, interacting with you, and that is a good chance, a golden chance to get your doubts cleared. Yes, Muli, we'll be sharing the collab link as well. Okay. So I guess Sagnik is saying I'm relatively new in the terms of NLP. This was so informative. Thank you so much. All credit goes to Sami for such an amazing live session. Okay. Fine. We have feedback pouring in. Yeah, Sami, you are saying something.
No.
Please go ahead.
No.
Okay. So you've been talking about the feedback link. So what we have decided, okay, Pakhar is saying, Samir, sir, thank you so much for your effort. Content was very useful and informative. Yes, even I do agree on that. Okay, Prashant has been quite obsessed with the feedback link. So Prashant, so let's do one thing, okay? Instead of collecting feedback through some link, let the people know, publicly about your feedback. What do you think about the content or the presentation, that we just held? Okay, so I'm pasting a LinkedIn company page. Let me know if you guys are able to access that link. Okay, and on this company page, you should see the live sessions poster on the page. Okay, so what you can do is you can put down your feedback in the comment section of that poster. So this exercise will do one thing. It will help others also to know about this session, like how did the session go. And if somebody do not know about this towards machine learning.org initiative, then they can get to know through your feedback, through your review, and they can make up their mind, whether they would like to attend the next live session or not. And second thing is, if we have the good interaction on our LinkedIn page, then it will help us to apply for the LinkedIn Live as well. So if we, if we are able to conduct our live session through LinkedIn Live, we'll be able to go live on the LinkedIn without asking people to register for the session, because our major audience lies on the LinkedIn compared to any other social media platform. So I'll humbly request all of you guys to, like, comment, share, and spread the words about these regular live sessions on your LinkedIn timeline, so we can continue this initiative in future also, and we can empower the data science community. Do you guys follow me? Can you put down your thoughts in the chat window? Do you guys think that's a good idea to put feedback? Okay, Anushka is saying, yeah, sure, sir. Okay, Ankush, yes, sir. Okay, thank you, Ankush. Thank you, Anushka. And you guys have been worried about the collab link. You've been worried about the recording, whether the recordings would be available, whether the PPT would be available. So we'll be doing one thing. We'll be processing this live session video, and we'll be releasing this video on the LinkedIn page. So you guys will be able to go back and refer the content, making sure that you can, you can play the video once again and see, if you haven't understood something in the whole live session, and you could go back and see if you guys could get it right. And if at all you guys have doubt about something throughout the live session, I mean, whatever being discussed in the live session, you can always put down in the comment section of that recording that you will be releasing on the LinkedIn page sooner. Yes, Anushka, yeah, very good point. I guess you have attended the last live session as well. Yes, so we'll be releasing that content also very soon on our LinkedIn page. So make sure that you guys are active on the LinkedIn page. So certificate and all, there is no certificate. See, that's where the catch lies. Okay, so major data science institutes would rip your pocket. In the name of a certificate or data science certificate. Here you guys get the knowledge free without a penny charged. Okay, so there is no certificate as such. So if I speak from my experience, I have worked into the corporate for so many years now, and if I sit in the recruitment panel, then more than the certificate, we look out for the knowledge, whether the person carries the knowledge on some particular topic or not. Okay, if you do not have certificate, and if you could still show the knowledge in the ML, NLP, or deep learning, we would be pretty much impressed by that, rather than just looking at the pile of certificates that you have mentioned in the in your CV. So I'll highly suggest not to focus on the certificate much, but to give more weightage to your learning. Okay, learn as much as you can. Attend all the live sessions that we'll be conducting in future also, and there's lots of information available on the internet. Make sure that you guys do your thorough research on each topic to make sure that you guys are clear with the concept. Yeah, Anushka is asking, is there any internship or project work running with towards machine learning? So yes, in a nutshell, we do have internship opportunity with us. And you can who shall I connect you with? Maybe I'll let the HR connect back with you if you're interested in the internship. Prince is asking what kind of internship. Okay, so what we do in the internship is, the Samir has been doing internship with us. Ankush has been doing internship with us. So these people carry profound knowledge in the machine learning and AI. So we just help them, giving them the right pointers in particular ML topics. And these guys conduct thorough research to make sure that they are thorough with the concept, ML concept or NLP concept or deep learning per se, and the same knowledge these guys are sharing with you. And we do make sure that anybody going live on some particular topic, they themselves understand the topic pretty much. So what I have personally found, or people in the IT industry find bit troublesome is, people know a lot of people know lots of things, like what is random forest or what is vector space model, but there are very few people who know why random forest. Okay, there are lots of classifiers, there are lots of regression models available. Why shall one go for random forest model only given some certain data set? Or if one algorithm works in certain manner, how does it work in that manner? So we focus on those concepts that many of the people miss on. So that's the internship all about, Prince. In nutshell, you get paid for your own learning. So yeah, we make sure that people who are working with us are corporate ready by the time they complete their degrees. I know it's a big word to say, making somebody corporate ready, but yeah, that's what we strive to do. Okay, yeah, thank you, Prince. Any other question to Samir, to me, about the session maybe? Where can we get the collab links? Would you please share? Okay, so what we'll do is we'll publish article keeping the same content, okay, on our website. If you guys haven't have opened our website, then I'll highly recommend to go to our website and subscribe to our newsletters as well. So whenever there's new blog coming up or new article coming up on any ML or NLP topic, you guys will have quick access to that information. So this collab, Google Collab notebook will also be shared on the website, Vishal. however it is there in the recording, you can always go back and check the recording. But for the quick access, you can check the website. Does that help you, Vishal? Okay, thank you, Vishal. Okay, any other question before we wind up this session tonight? It's been already 10:30. We have crossed half an hour.
Sir, kindly share any research areas in machine learning, NLP, any other trust areas.
Okay, could you identify yourself? Who am I speaking to?
This is Ajay, sir. This is Ajay.
Hi, Ajay. So yeah, please repeat your question. What you were saying?
Kindly state us any research areas which is related to machine learning or DL or NLP. These trust areas.
I'm still missing what you're asking. You're asking to share some research areas, is it? Okay, research areas in the field of deep learning, NLP, ML. Have I got your question correct? Could you?
Yes, sir. Yes, sir. Yes, sir.
Okay. So what do you mean by research areas? Like, it's a quite a loose term or vague term. I mean, there are lots of topics that you could research upon. Or is there something else that you want to ask when you say research areas? You're asking which topic you could research upon, or something else? Okay. Yes, sir, where we have scope. Okay, Ajay. So let me tell you, okay, you have scope. If you are a data science enthusiast, you already have lots of scope in the job market. Okay, example, self-driving cars. Okay, so see, if I talk about the research areas, everything is, everything is a research area. So let's say some particular person has, developed an algorithm. Then you can always go back, check how this particular algorithm has been developed, and you can tweak the parameters, you can tweak the, whole model building process and see if you could come up with something new. That's one research area. If you talk about the self-driving cars, then I guess you are talking about something that is blooming in the market right now. So computer vision applications are something blooming in the market right now. This is like emerging field right now. So it's not necessary that you conduct your research in the area that is growing right now. You can always conduct your research in NLP field. You can conduct your research in the ML as well. So if I talk about LSTM, I guess Samir has spoken about LSTM in his session somewhere in between. Then there are lots of variations and variants of LSTM available in the market. People have used LSTM as per their need. Okay, what has worked out best for them. So that is also one of the research area you could work upon. If I'm getting your question right, let me know in the chat window, or you could unmute yourself. Okay. So there's nothing, explicit as a research areas. Like whatever you are studying, that is your area of research. Okay. So make sure that whatever you're studying, you're thorough with it. Data scientists are not meant to just import the libraries, or modules from sklearn or Genesim or some other libraries per se. Any software developer would do it better than us. Okay. So when you call yourself as a data scientist, then one of the interest should be research. Okay. And what is research? You pick up any topic and you start reading a lot about it, making sure that you have the thorough understanding. Try to publish research papers as well if you have done something new. Okay. Okay. So any other question before we wind up the call? If you guys do not have question, you can drop no in the chat window. If you guys have question, please unmute yourself. Or if you're uncomfortable speaking, you can put down your question in the chat window. Whatever works out for you guys. No, Ankush says no. Okay, thank you, Ankush. Ajay, no sir, thank you. Thank you, Sagnik. Okay, Prakhar says no. Okay, then I guess we are good to wind up the call. Anything from your side, Samir, that you would like to talk upon, or anything that you would like to share before we wind up this call?
No, sir.
Okay. Okay. Thank you so much, Samir, and thanks to all of you guys, for taking time out and attending this live session. I'll humbly request once again to to be active on our LinkedIn page, so we can drive this initiative in future and can empower the data science community, in the future. Pleasure is ours. We support you. Thank you so much, Ajay, for your kind words. Okay, bye bye. Good night. Take care.